All right, and we are live.
Yes. Oh, really?
I got 2 people watching already.
Two people watching.
Already, like and subscribe. So, before we get into that, let's do Tendi. Get out of that homework. We're going to take a gander. Have plenty of time to get it done, plenty of time to work on it, so that's exciting. I am back. I am once again an uncle. Alrighty. McQueen. Don't dare stop. Alright. Right here. Hey, speak no evil.
Mr. Mac, I was up here to retreat thing.
The blind thing?
Yeah.
Oh, okay. How was it?
Hey.
What did you put for the sensor on the back?
I don't care.
The blind retreat was very uncomfortable.
Alright, does everybody have a worksheet? My eyeball.
You have to like give me.
Yeah, that's huge. Alright. Thank you. Looks like nearly everyone is in attendance. That is present. Alright, Alright, here's the deal. Starting out the worksheet. I'm going to shut the door now because I think everybody... perfect timing. Alright. Good enough. Alright, so homework is this. I got lazy with the answer key. Hopefully you did not with your own homework. But the main thing I need to see are the reasons, right? The algebra is not why we're here. The reason for the season is the geometry part, which is justifying your reason. So we're going to go over that pretty quickly. It's going to be out of 21 points. I do, for everything here except for one of them, need to see given. I was leaning in on one because there was a lot of steps, and I felt mercy upon you. Yeah, so the three things I need to see for number one are given, property of subtraction, and division property, right? It doesn't matter what order, because you could have subtracted first like I did, or you could have divided first. Now, if you divide first, right, that's no prenup, which means everything has to be divided up, right? So we divide the 2x by 2 and get x. We divide the 5 by 2, get 5 halves. 17 divided 2, we get 17 halves, which ain't no thing, because then when you subtract that 5 halves over, you have 17 halves, you're subtracting 5 halves. You're left with 12 halves, which is in fact 6, right? So you could have divided first. I just prefer to get the prenup, right? Remember Kanye? So I subtracted first. That way everything's out of the house when I'm ready to divide. That way I only divide 2 things. When I do that, I get 6. It's kind of convenient, right? But again, what I want to see is subtraction property, division property, and given for 3 points. Trade and grade. Who needs pens?
Are we allowed to fix it or no?
Yeah, go ahead. And then trade. And fix it later. The whole point is, do you see the mistake you made and why? Who else needs a pen?
I didn't write given.
Like your hair. Yeah, I know. You're probably like, I woke up this way or something, but like, I enjoy it. Number 2, check it out. So first of all, they give you the stuff. So write it down. What they gave you is this, right? So that's given. Then you're going to do addition to move the 7. Could you have divided by -3 first? Sure, knock yourself out. Could you have multiplied everything by -1? Sure, knock yourself out. The most efficient way of doing it would probably be to do the addition property first and then division. Those are the 2 big ones I need to see. You can't get away with it. No matter how you did it, you'd have to do 2 of those. And then you'll find out that x is indeed -7. So those are the 3 things. 3 points on that one. Number 3, given that this, right, prove the thing. So they give you the thing, make sure you write the original. Addition property to move the 3, and then multiplication property to move the 2, right? That's the idea. Again, could you have done it different ways? Sure. I don't care. But those are the 2 main things I need to see, along with given. 3 points. Questions, comments, concerns, other than for my mental stability?
No.
Wonderful. Flipping the page. Number 4 says A, B, and C are collinear. Yikes! We got a lot of stuff going on here, right? Making sure you can see it all. So A, B, and C are collinear. Collinear means what?
And a line.
And a line. Same line. Very good. Co means same. Linear means line. Well done. AB they give us. BC they give us. And AC they give us. So I made a diagram and said they gave it to us, right? We're trying to prove that BC is 1. We're trying to prove that BC is 1. I'm going to repeat it one more time. We're trying to prove that BC is 1. And so what I did is I realized, look, we're trying to prove something that's an equation. Well, how do I do that from a diagram? Well, I need to get an equation. So how do I get my equation? Segment addition postulate, right? 2 things added up equal the whole thing. And then from there, I need numbers, so I probably should get rid of those and replace them with numbers. Did it. Substitution property. You picking up what I'm putting down?
Yes.
So far, so good?
I suppose.
All right, and then we do math, which we don't need to justify. That's why I put the therefore symbol. Negative x plus 2 equals 5 because negative 2x and x makes negative x. 7 and minus 5 makes 2. 5 is already on its own. And then the next step is to do subtraction, so I can get rid of that 2. And then divide or multiply by negative 1, same thing. And then you'll get this, right? Did I show my work here? No, I didn't. Ain't nobody got time for that. But I need to see these things, okay? Don't worry about given for this one. There's a lot of steps. I know the given on this is a diagram, which is kind of confusing. So there we are. X is negative 3, and we're done, right? No, because we want to prove that BC is 1. We want to make it look just like that. So what I have to do is go back to the givens and realize that BC is negative 2x minus 5. So I write that. BC, given, negative 2x minus 5. By substitution, I can switch out x for negative 3. I need to see subs with an S, not just sub, because that could also be subtraction, right? We have subtraction, or I'm sorry, subtraction and substitution here and here, right? And then when you do the math, negative 2 and negative 3 makes positive 6. Minus 5 is a positive 1, and that is BC swag box.
How much is this?
So 1, 2, 3, 4, 5 points on this one. Ignore given on this one. Don't worry about
The
it.
substitute, the box.
The subs?
2 point, the box. What's it called? The answer box?
Oh, the swag box? No, it's not worth anything. Worth absolutely nothing, but it's important. All right, next one. Given D is in the interior of ABC. So imagine an angle ABC, and D is in the interior. Interior means what?
Inside.
Inside, internal, like the voices I ignore most of the time, right? So ABC with D on the interior, there it is, okay? They tell us the different angle measures. ABC is the whole dumb thing. It's 165. I did that in orange. ABD is this bit right here. I did that in red. It's x over 3 plus 45. DBC is the blue part. They told us it was 3x plus 20. And that's given to us, okay? I'm going to count given on this one just because I felt evil. I felt like I gave you one. I can't give you both. So here we are. Angle addition postulate gets us the equation, because again, we want an equation. We want to prove that the measure of angle ABD is 55. I'm going to say it one more time. We want to prove that the angle measure of ABD is 55 degrees. So we need numbers and we need an equation. So there's my equation. My numbers come from substitution. You picking up what I'm putting down? Find the pattern here. Don't skip step 1. You can't just say this stuff, because what if we're not measuring in degrees? Right? The angle addition postulate doesn't say that degrees plus degrees equals degrees, because not always do we measure in degrees. Right? It's just saying whatever the measure is, they're going to add up to the big guy. And then after that, we can do substitution, depending on what we're measuring in. So now we're here, and you, of course, knew 45 and 20 make 65, no big deal. But did you know that 3x and x over 3 is 10x over 3? Did you know? Well, think about it logically. We haven't talked about common denominators in here, really. But you can think about them logically. So how many thirds? Because this guy's talking thirds, right? How many thirds are in the number 1? How many thirds are in the number 1?
3.
3 thirds, right? That makes sense. How many thirds in number 2? 6 thirds. How many thirds in the number 3?
9.
9 thirds. And that makes sense, because if you write 9 thirds, remember division is fractions are just division for lazy people. 9 thirds is 9 divided by 3, and that is 3. They're one and the same, just a different way of looking at it. And that's what algebra is all about, getting new perspectives, and couldn't we use more of that? So don't think of this as 10 thirds. Think of it as 9 thirds. If I have 9 thirds and 1 third, and I'm adding them together, how many thirds do we have? 10 thirds. 9 thirds plus 1 third is 10 thirds. Okay. We'll talk about the algorithm to figure out common denominators later, but like most of the time you can just do it in your head.
Like a Rubik's Cube.
Right? If that's 5x and that's x over 3, how many thirds are in the number 5?
1.
Try again. How many thirds are in the number 5?
2 thirds. I don't know. 15.
15 thirds. So I have 15 thirds and a third makes 16 thirds, right? Again, you can do that in your head. 3 thirds is 3 is 9 thirds, right? It's the same thing. If you write it out, 9 divided by 3 is 3. It checks, right? So it's going to be 10 thirds. 9 thirds, 1 third is 10 thirds. Cool. You could have written 10 over 3x or 10x over 3. I don't care. Then we're here. We're going to subtract the 65 by subtraction property of equality. And then we're going to multiply by 3 and divide by 10. Or multiply by the reciprocal if you're feeling fancy, right? I multiplied by 3, multiplication property of equality, got this, and then I divided by 10. You also could have divided by 10 first, right? Check it out. If I divide this by 10, I get x over 3, right? If I have 10 thirds and I divide it into 10 pieces, 1 third, right? Divide this by 10, I get 10. Now I get rid of the divides by 3 by multiplying, and I get 30. So you can divide by 10 and then multiply by 3 if you want it. I don't care. I bet most people multiplied first. I like to get rid of the division when I see a problem like that in the world. That's what we should do. And then we're not done because x is 30 doesn't match up with what they wanted, right? They wanted to figure out what angle measure ABD was. They told you it was 55. So we go over here. Given that ABD is x over 3 plus 45, we can then substitute 30 in. 30 divided by 3 is 10. 10 and 45 is 55. Oh no, you can't see it. Please tell me when you can't see things. I'll try that again. So I wrote that given measure of angle ABD, this was given to us, x over 3 plus 45. I can plug in 30 by substitution, S-U-B-S, right? 30 divided by 3 is 10. 10 plus 45 is 55. How you feel? Dece? Okay? If you made a mistake, do you see why you made a mistake? And if you don't, now's the time to raise your hand. And if not, come see me, right? Feeling okay? Or absolutely not? I can't tell if you're bored or lost. Rosie, you're lost. Wonderful. So here's what we do. We play a game, okay? Instead of asking, what did you do? Because that could be anything. Thank you very much. What we're going to ask is, where did you go wrong?
I don't know.
All right, so here it is. So far, Rosie, diagram. Match up to yours? Or did you not make one?
I did not make one.
Wonderful. Okay, fantastic. That's skippable. What about this one? How's the setup there? We match? Yes or no?
See, it's not
Blank. Okay, wonderful. All right, so here's the idea, Rosie. D is in the interior of ABC, so I drew that. Right? That makes sense. D is in the interior. They told us ABC, whole thing's 165. Don't write it down. Watch. They told us ABD is this, and they told us DBC is that. Cool? All right, sure. I know that the two little guys should add to the big guy. That's angle addition postulate, right? Cool. Then I have this. I substituted their values, right? ABD is that, so I switched it. ABC is 165, so I switched it. CBD is 3x plus 20, so I switched it. Smell what I'm stepping in?
Yeah.
You have nothing on your page. Why are you looking down? All right, now we're here. Put stuff together. 45 and 20 is 65 all day. That's 9/3, and that's 1/3, so that's 10/3. So I'm with you there.
Yeah.
Wonderful. Okay, next, do math. Subtract 65, multiply by 3, divide by 10, and we're x equals 30, okay? Last little bit over here. So they want to know what ABD is. We found x, but we didn't find ABD. So I said, given that ABD was given to us as x over 3 plus 45, and they did give us that, right? I can plug in something for x. We call it substitution. I plug in 30. 30 divided by 3 is 10. 10 plus 45 is 55. Do you see what's going on here? We're done.
Yeah.
That's it. Thanks for asking. All right, 12 on that side, 21 on the front. I'm sorry, 21 in total. If you like your grade, turn it in. If you don't like your grade, since I...
So I'm gonna turn it in.
I'll just turn it.
1, 2, 3, 4, 5, 6, 7. If you like your grade, turn it in. If you don't like your grade, correct it and then turn it in.
Do we turn in L warm up?
Yes, warm-up-os, yes, turn them in.
You make fun of me too. That's equal.
We've only done like 2 warm ups.
I know. Next week we have an early dismissal on Wednesday. I figured we'd take this week easy since I've got a lot of stuff going on with my sister and all that. And then you guys had a lot of stuff going on with blind. So we kind of are combining these 2 weeks into a quiz next week. First question.
How many points was number 3 worth?
Number 3 was worth 3. So 21 points total, yeah.
So that homework assignment online was like not a thing. So I just did that.
So can I turn in the
I was
pages
so
I did?
mad. I didn't even do it. I gave up.
Can I turn in the pages I did?
Then do it.
To get
I was
some
so
points.
There's always self-development. Yeah.
You ain't gonna do that.
I think I got 2.
Turn it in for self-development.
What are we doing Wednesday? 'Cause I'm not gonna finish.
Go. Wednesday? Since it's early dismissal, probably not a whole bunch.
I gotta find
Next Wednesday's an early dismissal, which means
Why?
we'll have Monday and Tuesday to learn stuff, kind of add on to what we're doing already. And then Friday we'll have a quiz that covers all this stuff, okay?
Don't touch the next.
I didn't know.
Don't touch it.
All right, today what you need to do is get out your proofs toolbox. We're going to be looking, open up your hymnals to where it says by definition.
I've been here in football.
That's
You
right.
commentating tonight?
I don't know, probably not. I haven't been yet. I know. This is the big deal in Podunk, Illinois, right? So I might. I'll think about it. But I'm also very tired because like my sister had a baby and I had to like be there for stuff. And, like, again, that's right. Yep. Once again, yep.
Yeah, so congratulations.
Isn't there a guy called DJ Mac?
I know. I worked so hard. All right. First, I would like to thank all the little people, especially that little one.
All babies are.
Babies are ugly by definition. Speaking of by definition, by definition is how we're going to prove some things, right? How do we know something is opposite ray? Well, if it fits the definition, then it is, right? How do we prove that my name is Derek? Well, because I fit the definition. I was defined at birth to be Derek, right? So I fit the definition. It's not complicated. So if something's really obvious and it just fits the definition, we say, oh, by definition is why it is, okay? So let's talk about some definitions. First of all, by definition, sorry, I'll zoom out. My handwriting's big enough, I believe. Okay, so here's where we are in our hymnals. Opposite rays is what we're talking about. Hi, Ray. If two rays, hi, Ray, share an endpoint, that's where the rays begin, is the endpoint. Figure that one out. Forming a line, then those rays are said to be opposite. So check it out. Here's two rays, yx and yz. They share an endpoint, endpoint y. They form a line, x, y, z. X, y, and z are collinear. Therefore, we call these rays opposite because they're heading in opposite directions. Now, words are hard, but math is easy. Do you see what this is? Do you see the opposite rays? Do you understand the logic behind why we call them opposite?
Yeah.
Right? Okay? Then you know it when you see it, and that's all that matters, right? There's this big thing in the 90s called the porn wars, right? And it was about this porn rock that came out. And it wasn't literally porn, but it was like things that were, they talked about in rock and roll music that was really like obscene. And again, this is the early 90s, right? We were very, and so they went to Congress with this, and they were trying to pass laws to ban certain types of music. And so they brought in Frank Zappa and guys from like 9 Inch Nails and Marilyn Manson and all these people. 9 Inch Nails wasn't there? I don't think 9 Inch Nails was there, but Marilyn Manson I think was. And so they went through and they read all these lyrics, right? And at the end of the day, what they decided was, is this judge, he's like, I don't know how to define pornography, but I know it when I see it, right? So as long as you know it when you see it, it was good enough for them, it's good enough for us, okay? Don't need to know the words. Do you know what opposite rays are when you see them? Wonderful. Excellent. It turns out they weren't able to pass a law on that. They got the parental rating thing on there. That's where that all came from. But they weren't able to ban the music. Thank God. All right. No. Linear pair. What is that? Well, linear means what?
Same line.
Line! No, collinear means same line. Linear just means line. Pair means two. It means together. Aww. So, if two adjacent angles, adjacent means next to. If two angles that are next to each other whose non-shared legs are opposite rays, we know what opposite rays are, those two angles form a linear pair. Now check it out. Words are hard, math is easy. Check out the diagram. We have two angles here that I'm talking about, x, y, q, this one right here, and we have q, y, z, this one right here. They are on a line. They're a pair. They're together. And there's two of them. And they're non-shared legs. Notice that they share this leg, right? Aw, it's like a three-legged race, right? So they share this one, but they don't share this or this. Those are their opposite non-shared legs. So those non-shared legs, are opposite rays. Ladies, are we all right? Okay, what we're talking about has nothing to do with this, and it's loud enough where they can't hear me, which is a problem. So either be quieter, or we have the technology, right? Text them. So yx and yz are opposite rays. These angles are sitting on a line together. They are a linear pair. They're on the same line, linear pair together. Two of them on a line. You know it when you see it, right? Wonderful. Song of the day on Monday is going to be Porn Wars Deluxe by Frank Zappa, I think. That's going to have to be. Frank Zappa is a rock and roll artist, but also jazz. I don't know what you're talking about. Moving on. So, linear pair. What's special about linear pairs and opposite rays? Right? Because who cares if they're just a definition? What can we do with them, right? Why is this useful to me? Theorems. We have two, one of which you know, the other which you don't really yet. But we're going to get into today. Linear pair theorem. So if you have a linear pair, we know something about it. What do we know about it? It says if two angles form a linear pair. So if there is a linear pair, then we know that those two angles are supplementary. Now, why don't we say that they equal 180? Well, because not always do we measure in degrees, right? Sometimes we measure in radians. So we want something that's more universal. So saying they're supplementary, that gets the job done, right? If they're supplementary, therefore we know they equal 180, right? But that's a little bit further. So two angles are a linear pair. If they are, like this one is, right? 4 and 3 are a linear pair. You know it when you see it. They're going to be supplementary because they're on a line, right? We can prove that because this is a theorem. It's not a postulate. Remember, postulates we believe because how could they be anything else and there's no way to prove it? We tried, right? It's just a foundation of mathematics. We have to take a leap of faith. These can be proven. And we're going to do that today. We're going to prove this theorem. And then once we've proven this theorem, we no longer have to prove it anymore, and we can just use the short. The short and the sweet is angle 4 and 3 are a linear pair by definition, right? They fit the definition. I know it when I see it. Therefore, they must be supplementary because linear pair theorem says so, right? Why are they supplementary? Oh, well, linear pair theorem says so. I don't care, right? Today we do care, and we're going to prove why that's true. Why do these have to equal 180? Okay? We're going to get to that. Let's do that now. You have this. You do not have this. I'm going to repeat that. You have this. You do not have this. So if you don't see it, good. Okay? It's up there. So here we are. Proving the linear pair theorem. First of all, it says if we have a linear pair. So let's have a linear pair, right? Let's talk about a linear pair. Here's my linear pair. I'm going to define it. I'm going to put letters on it. That way we all know what we're talking about, right? Let these two angles be a linear pair. We're not given that, right? Like we are in a homework assignment. We gave it to ourselves. Let this be, right? Let there be one. So we said, these guys are a linear pair. Let it be true. Here's my diagram. Now you know what I'm talking about, okay? What are we trying to prove? We're going to try to prove that this angle right here, the purple angle, MJK, is, and MJL, this angle right here, the blue angle, are supplementary. That's what we're going to prove. Did I write any numbers down? No, I don't know that it's 50, that's 130. I don't know that. I don't need to know it because I know they're a linear pair and I should be able to prove that they're supplementary. I don't know what, individually what they are, but together, they're 180. Ah, beauty.
You can see it.
Yeah, you can, but we're going to prove it because we can prove it. It's not a postulate. It might seem like it is because it's so obvious, but it isn't. We can prove it. Here's what we're going to do. Okay? So, a lot of stuff. I'm going to cover it up one at a time. You're going to follow along with me. Eyes up here, I swear to God, if you're writing stuff down. Why? Okay? So here we are. Okay. Here's the diagram. Everybody see it? Yeah. So step one. Here's my logic. Here's my logic. Follow if you can. Ray JK and Ray JL. These guys, right, are opposite rays. You know it when you see it. Definition, right? By definition, they are. Of course they're opposite rays. How could they be anything else? Moving down. If they're opposite rays, therefore, those opposite rays form a straight line. Makes sense if they're going in complete opposite directions, right? By definition, pretty much. They're going to be a straight line. Now, what do we know about straight lines? They form straight angles, right? By definition, that's a straight angle. And what do we know about straight angles?
Straight.
That's right. What are they measured? 180. Do you see where I'm going with this? Because if I can prove the whole thing's 180, I can prove the pieces are 180. If the pieces are 180, then they're supplementary by definition.
Yep.
So this is part one. I'm going to walk you through it again. Follow with me. JK and JL, opposite rays. How do we know it? Because it fits the definition, right? They're opposite rays. The rays going in opposite directions. They share an endpoint, yada, yada, yada. Okay? I know it when I see it. If they're opposite rays, then I know automatically they form a straight line, right? That's just how things be. Therefore simple. Don't need to justify it. It just is. Sometimes it do be like that. Next one. Angle KJL. That's this guy, right? That's KJL's angle. Must be a straight angle. If it's a straight line, it's a straight angle, right? Makes sense? Definition for straight angle. I know it when I see it. Lastly, for part one, therefore that angle I was talking about, KJL, must equal 180. By definition, right? Straight angle. Straight angles are always 180. Just like a right angle is always 90, straight angles are always 180. Questions, comments, concerns, other than fundamental stability?
No.
Wonderful. That's part one. So I've established that the whole dumb thing is 180. That's good. Because if the whole dumb thing's 180, don't the pieces have to add up to 180?
Yep.
Why is that true? Why do the pieces have to add up to 180?
Because they're on the line.
What postulate says that the pieces have to add up to the whole angle?
There are supplementary.
Any predictions?
Segment something.
We only have two postulates.
Segment addition.
Not segment addition because we're not talking about segments.
Angle.
Angle addition, right? The pieces, the angles, the pieces of the angle add up to the whole angle, right? So I'm going to use that next. So check it out. There was part one. A little bit higher. Right? That's what I left off on part one. I needed that information, so I'm letting you see it, okay? Here's part two. Yikes, what's going on there? No big deal. All I'm saying is that MJK, that's this angle, plus the other angle, equals the whole thing, right? Duh. Now how do we know that? Angle addition postulate says we can do that. If we break up an angle, the two pieces add up to the whole thing, right? It's still the same thing. Are you with me? Next thing, check it out. I know that KJL is 180, right? I learned that from part one. Here's KJL. So wherever I see KJL, I could switch out 180, couldn't I? If I tell you X is 5, can't you switch out X for 5? Well, I told you KJL is 180. So where I see KJL, I can switch for 180. Why did I do that? Because now I've got the two angles add up to 180. Ah, we're almost done. Now remember, they want us to prove that it's supplementary. We've proven they add up to 180. It's close, but it's not exactly the same thing, right? I want it like word for word. So our last step, after we've done substitution to switch out KJL for 180, is to say by definition, that's supplementary, man. I know supplementary when I see it, right? That's supplementary. How do I know it? Well, that's the definition of supplementary. If two angles add up to 180, they're supplementary, by definition. I hope so. This is new. This is different. There's no PEMDAS. There's no rules here. There's no structure. There's no do this, and you win, right? There's lots of ways to do it. It's scary. And the only way you're going to get good at it is if you try it over and over again and get used to seeing what you need, right? To be able to draw a roadmap from A to B. We knew where we needed to go. We knew where we were starting. The question is how we get there. And a big way of doing it is writing down what you know, right? Maybe seeing the idea. If I want it to be supplementary, I need to prove that these two add up to 180. Well, how can I prove they add up to 180? Well, if they add up to the whole thing, then they're 180. How do I prove they add up to the whole thing? Angle addition postulate, right? Sometimes working backwards. I'm going to walk you through this again in slow-mo. Again, if you're watching at home, hi, you can pause and rewind. Check it out. Step 1. JK and JL opposite rays. Know them when I see them. Definition, right? Next. Therefore, they must be a straight line. Am I blowing anybody's mind?
No.
Therefore, KJL is a straight angle, and straight angles always measure 180. Part 1, we got it, right?
Yeah.
Third time around, we're about 50 to 75%. I'll take that, okay? Next. Let's go up a little bit further. So we know that KJL is 180. That's where I left off. Family, come on. KJL is 180. I also know by angle addition postulate that the two little angles add up to the big one, right? You need to get used to using angle addition and segment addition postulate, okay? That's what gets you the equations. Then I can substitute 180 for KJL. Everybody seeing that? Thomas, you seeing this? 180 KJL, we can switch them out?
Yes.
Okay, wonderful. So that's substitution. That's the switch out property, right? Therefore, that's supplementary, right? Swag box, we're done. How do you feel?
Easy.
Dece? Okay. It should feel weird. If it feels easy, that's great. That's probably because you're underestimating it.
Yep.
If it doesn't feel easy, that's okay. That's normal. This is day 1, guys. It's going to take a while to get used to this stuff. It's a whole different thing. We've never had you guys actually think about what you're doing in class, which is a shame because we could have been doing this since like elementary school. Right?
Be ahead.
You would be where you should be. I apologize for that. Now, check it out. What we're going to do on Monday is we're going to do this. It's the same dumb crap. The same dumb crap, except instead of doing it like this where it's like an outline, it's written out. This is an actual proof. So check it out. We're given this. By definition, those guys are opposite rays, right? Thus, they form a line. By definition, that must be a straight angle then, right? Thus, that whole thing's 180. Sound familiar? Okay. Part 2. All the pieces add up to the big one. Segment or angle addition postulate. By substitution, I can switch out these guys. Again, check it out. This guy is 180, so this guy is 180. Okay? Colors help. You need to get markers or pens. This will help you a lot, okay? Therefore, by definition, those are supplementary. End proof. That's what we wanted.
Swag.
Okay? Swag box. For now, we're going to do the outlines, okay? And we're going to formalize it later. All right, so check it out. What we're going to prove now is the other theorem we have. This theorem you have not learned about yet. We're going to learn about it right now. So we already did linear pair theorem, right? And we proved that. These guys have to add up to 180. They have to. They're going to be supplementary. Has to do with opposite rays and all that jazz. Vertical angles theorem. That's the new one. So what are vertical angles? Great question. I'm glad you asked. Check it out. Open your hymnals up to where it says revolution angle at the top. At the bottom it has vertical angles, has a little diagram. We're going to talk about what those are. You know what supplementary, complementary, and revolutionary are. But vertical, that's a new thing. Okay?
Whoa.
All right, so check it out. Gotcha.
I did that.
Words are hard, math is easy. It says if angle 1 and angle 2. So two angles, okay? We're talking about two angles here. If they're formed by two intersecting segments. So check it out. Down here, I have two segments that are intersecting. They're lines, I know. But imagine if I put dots. And I can do that, right? Lines are just segments that are extended, right? They would intersect, and they'd be called intersecting segments. So I said segments because that's more specific, but lines work too, right? So two lines intersecting. They form two angles. 1 and 2 is what I'm talking about here. If those angles that it formed, the ones you're talking about, angle 1 and angle 2, are opposite angles, opposite means across from each other. Adjacent means next to. See how 1 and 3 are next to each other? That's adjacent. Opposite is across. You smell what I'm stepping in? Okay, cool. So if we have two things that intersect, and they create angles, and those angles we're talking about are opposite angles, then we can call those vertical. That's what a vertical angle is, okay? And vertical because they're up and down. Now, 4 and 3 are also vertical angles because if you turn it, ta-da! Yeah, so it's kind of a bad name because they're also like horizontal angles, right? The way I like to think of it, and again, the proper name is vertical angles. You do need to know it. I like to think of it as scissors theorem, okay? So imagine a pair of scissors doing this, right? Okay, so these guys, as my 5th hour put it, these guys are buddies, 1 and 2, right? And so they're, yeah, here we go, right? So if you notice, these are 2 segments that are connecting, right? They intersect. How do they intersect? Well, any way you want, right? So if I intersect like this, the angle on top and bottom are the same, right? And even as I close this angle at the bottom, notice it closes the angle at the top. Is this making everybody nervous? Just a little bit? No. Keep going. Okay. All right. And notice the side angle is the same thing, right? As I make this one bigger on the side or smaller, the other one responds, right? So they work together. Side angles are the same. Top and bottom are the same. Vertical angles theorem says that. It says if you have vertical angles, the 2 top and bottom ones are going to be congruent. Okay. So vertical angles, the definition just says that's what a vertical angle is, right? Vertical angles theorem says not only are they vertical angles, but vertical angles are always congruent. So how do we prove that? Because it's not a postulate. There must be a proof behind it. Well, I'm glad you asked. So we're going to prove vertical angles theorem. It says if we have 2 vertical angles, and by definition, those are vertical angles, right? They fit the definition. Therefore, they must be congruent. How do we do it? Again, great question. I'm glad you're asking. The participation in here, top notch today.
We know.
We've declined.
Yes. Which is what you guys should do every time the other team gets a penalty. All right, here we are. Proving vertical angles theorem. How do we do it? So, first of all, we need to set up some vertical angles to talk about, right? Because we're not proving the definition of vertical angles. We're proving if we have vertical angles, they'll be congruent, right? So let there be vertical angles. Let's put some names on them. I called mine XYZ and AYB just because I did. Here's the diagram. Check it out. XYZ, AYB. These are the 2 angles I'm talking about. By definition, they're vertical, right? They're opposite. Not adjacent, but opposite. So given that, right, let that be. We're going to prove that XYZ, the top guy, equals AYB, the bottom guy. Questions, comments, concerns? Wonderful. So how do we do it? Here's the logic before I get into it, okay? Here's the logic. If you haven't been paying attention, some of you aren't, pay attention now. Guys, this is geometry. This is not algebra. You can't just catch on later on, okay? You have to follow it as it goes. That's why I don't want you writing stuff down. So if you're screwing around, don't. Why? Not because I care about your grade, but because you're going to come whining to me later for help. And I will help you because that's the type of person I am. And it will be so annoying, but I'll do it, okay? So try and get it the first time. That way when you need help, you don't need 100% of the help. You only need like 50 to 75%, okay? So here we are. We start out with our thing that we know, and we're going to prove that these 2 angles are congruent, okay? So let's cover this up. I know you're intimidated. Start out with the given, right? Same thing I had in the last page. We cool?
Yep.
I've got a set of vertical angles. Vertical angles are opposite top and bottom. Here's the logic. What I'm going to do, okay? I'm telling you the trick before I do it. This guy and this guy, they're not vertical, are they?
No.
They're adjacent. If I do this, do you notice something about those 2 angles?
They equal 180.
They equal 180 because they are a
Jason.
what? Nope.
No, the
They're on the same line. There's 2 of them. A linear pair. There we go. They're a linear pair, which means they must be 180.
yes.
Ah, okay. All right. Now, check it out. What if I do this? Now we're cooking with gas, right? So here we are. These guys are a linear pair as well, right?
Yes.
So check it out. These guys equal 180, and these guys equal 180. What if I cut out the middleman? Then these guys must equal each other, right? Check it out. If that's 130 and that's 50, they equal 180, right? Well, if that's 50, then this has to be 130, right? So they're the same. That's the logic, but we're going to do it without numbers because it works for any set, not just when they're specially 130 and 50, okay? So here's the idea. Step number 1. I told you these are vertical angles, right? I established now that these 2 are a linear pair.
You don't have to.
You do not have that. Eyes up here. Watch up here. The magic is here, okay? So these are vertical angles because we said they would, right? That's what we started with. From that information, we can also say that these 2 are a linear pair, by definition, right? They fit it. They're 2 angles on a line. And if they're a linear pair, what do we know about them? They equal 180. They're supplementary, right?
Yes.
And if they're supplementary, right, that's linear pair theorem saying they're supplementary. And if they're supplementary, by definition, they must equal 180.
Yep.
Cool? Wonderful. Yeah, I should have by definition of supplementary here. But that's fair enough. So they add up to 180. You cool? Wonderful. Sorry for the bad handwriting. Yeah.
Is that like XYZ plus BYZ?
XYZ plus measure of angle BYZ, yes.
Aren't they both 180 though, being that they're just both straight lines?
BYZ is this guy? That ain't 180.
Oh.
Yeah, good question. The two, no, it's good. Please ask that, because other people are going to think it, and even if they don't, you thought that, which means that you're going to be stuck thinking like this doesn't make any sense. Because you're right. If that was 180, then it should be 360, right? And then you're lost. And not because it's like too hard, but because it's like you just missed it. You just didn't see it, right? That's a silly thing to have like lots of mistakes over. Thank you for asking that. Please always ask dumb questions, okay? That's what you called it, right? I mean, there are dumb questions, but every question is important, right? All right, so here we go. That's part one. I have established that these two add up to 180. Haven't said anything about these two, right? That's what we want to get to. But these two are 180. Now, by the same logic, this saves you a lot of time. By the same logic, these two must be 180, right? Same logic. These two are a linear pair. These two must be supplementary. These two must add up to 180. Now, instead of writing that all again, but just changing the letter names, I just said by the same logic, this is true. Oh, sorry, I skipped ahead. By the same logic, that is true. Do we get it? These two add up to 180 as well, by the same logic? Okay, there's one more step in part one. I forgot, my bad. So check out this equation. Angle plus angle equals 180. Now look at this equation. Angle equals 180 minus the second angle. So what did I do? I moved it over by the subtraction property. Ah, now it's all making sense why we learned that. I moved it over. That's all good. It's just another way of looking at it, right? Same equation.
Yeah.
And it makes sense. 180 minus that amount is going to get us whatever's left over. Right? I mean, come on. Now, why did I write this? Because now I have this on its own. That's important, okay? So, again, I know this about x, y, z. I can do the same thing for a, y, b by the same logic, right? The same logic. Again, these are a linear pair. Therefore, they must equal 180. Therefore, 180 minus this bit gets us this. You dig? I'm going to say it again. These two are a linear pair. By linear pair theorem, they must be supplementary. If they're supplementary, then they must add up to 180. If they're 180, I can take 180 minus this guy, and I get what's left over, this guy. Okay? That's what I'm writing here. Now, check it out. I have x, y, z, the angle I'm interested in, this guy, equals a bunch of junk. I have AYB, the other angle I'm interested in, equals the same bunch of junk. Look at this, 180 minus measure of BYZ. 180 minus the measure of BYZ. They equal the same thing. I'm touching the paper's touching the pen. Therefore, I'm touching the pen. He's touching that. He's touching that. Therefore, they must be touching each other. That's right. So, they must be equal. They must be equal. And that's what we're trying to prove, right? That these two are congruent. So by last step, I say, by the transitive property, I can switch these out. You could also do substitution. See how that's equal to that? So you can switch them out. Transitive property and substitution, basically the same thing. So therefore, they're equal, which means, therefore, they're congruent. I'm going to walk you through it one more time. Slow-mo. If you are confused, you need to look. Step one. This is what we're given. Okay? I want to prove that these two are congruent. So the way I go about it,
And when you say these, you mean the spaces.
these two angles right here. Yeah, good question. So check it out. This angle here and this angle here should be congruent.
Okay.
That's what I'm trying to prove. Linear pair, vertical angles theorem says vertical angles are always congruent. And those are vertical angles, right?
Accurate.
Cool. So now I'm going to prove that vertical angles are always congruent. So the way I do it is I say, these two angles are a linear pair. How do I know that? Definition, right? They're on the same line. See the line? Let me cover it up with a sticky note. See how they're on the same line?
Yes.
Those two angles? So they're a linear pair by definition. Which means they must be supplementary by linear pair theorem, right? Linear pair theorem says if we have linear pairs, then they're always supplementary. So those are supplementary. They add up to 180.
Equal 180.
Uh-huh. So I wrote that. Now from there, I'm going to subtract this guy over, and now I'm here. Okay? So I know that the angle I'm interested in is 180 minus that angle. Okay? Just another way of thinking about it. Step two, I do the same thing, but with these guys. These guys are a linear pair by definition, right? And if they're a linear pair, by linear pair theorem, they add up to 180. And if they add up to 180, then I can move things over, and I get this. Okay? Trust me, I know you're looking at the letters, and you're like, wait, I don't know which letters. Trust me, it's those two angles. I already pointed them out to you, okay? And I just moved the thing over. That's how BYZ got there, okay? I moved it over.
I'm
I'm sorry.
Now notice, last thing. Don't be sorry, just be quiet. This equals that, and this equals the same thing. So if this guy equals 5 and that guy equals 5, then they must equal each other, right? Well, instead of 5, we just have a bunch of junk. But it's the same bunch of junk. That's the important part. 180 minus measure of angle BYZ. 180 minus measure of angle BYZ. It's the same thing. So by the transitive property, he's touching the pen. He's touching the pen. Therefore, they're touching each other. By the transitive property, XYZ and AYB are equal. And if they're equal, they must be congruent. And that's what we wanted. Okay? It has just begun. So here's what we're going to do. The only way to get good at this is to practice it over and over again, and you're going to have to see proofs that you've never seen before. So here we are.
Oh my God.
We're going to do some together. I want you to take a gander at this. Now, I'm assigning it on Friday, which is breaking my rule, right? I promised you we'd never have homework on Fridays. I didn't promise. But I also promised you'd have a quiz every Friday. So you like when I break my rules, right?
Yes.
Yes, you do. Because otherwise you pull out the quiz right now. So here's the deal. Get over yourself. Here it is. It's not due. If I sign it on Friday, it's not due until next Friday. Okay? Are we going to go over it on Monday? Oh, you betcha. So no harm, no foul. Have you figured out how homework works in here? Everything's made up and the points don't matter, right? Why do we grade it in class? So you can get instantaneous feedback and you know you suck at it before the quiz. That way you can come and see me about it. But no one does that.
It's like Trish.
What?
All right. So, we're going to get some practice here. Thinking logically. You're going to start picking up on some patterns in some of these proofs, which is good. We're trying to get into a mindset of how to think about these things. There is no PEMDAS. There is no steps. There is no follow steps 5 through 7, and you'll get the answer. There never was. Somebody invented that. That's why they break it up into little like chapters and little sections in the book, because all those sections have the same steps. And that makes it easy for you guys. But it also coddles you. It makes it so you think that math is all about procedure. And it ain't. This is the beginning of real math.
Why don't they teach us this in the first place?
Great question. I think it's because it's too hard, and they don't want to try. And it's risky because the school system is designed to where if you guys get bad grades, then I'm not a very good teacher, therefore, and then I'm not here anymore. So the teachers that try to do this stuff and struggle with it because they take a risk don't get rewarded. So why would you do it, right? But I'm nuts. I don't care about my own stability.
We know you.
I do stupid stuff all the time for the greater good.
Yeah, I break one with my head.
All right, here we go. But like, that's like, has no purpose at all, I would imagine, right? So like, why are you doing it? Like, I'm going to play the saxophone backwards and play it like this. Like, great, who cares, right? But if you have a purpose behind it, like, oh, now that's art, right?
I didn't mean to break the. He was trying to get into the weight room. And
Boring, moving on. All right, so check it out. Given PQ equals RS. So they give us that PQ is RS. So we probably should mark that on our diagram. PQ and RS are congruent, right? The measure of PQ is equal to the measure of RS. They want us to prove that PR is QS. Now, first of all, what is PR and QS? I feel like half the battle here is figuring out what the heck they're talking about, right? So here's what PR is. PR is from P to R.
Oh, nice.
Now you see it.
And it's the same thing as
I'm always
QS.
backwards.
And that's what we're trying to prove. And QS is from here to here, right? So we're trying to prove that those bits are the same, which isn't super intuitive, but it is. And I'll show you why. So here's what we're going to do. We're going to write what we know. I don't know what we're doing with this. There's no steps. There's no plan. I'm just going to write what I know. First of all, we're given PQ and RS, right? They're congruent. So I'm going to write that. PQ is equal to RS. And I am given that. So I'm going to write given. Okay? And again, my goal is to get PR and QS to be equal to each other. So I need to take this and somehow turn that into a PR and a QS. So how do I do that? Well, check it out. What else do I know from this diagram? Let's talk about what QS and PR equal. So PR equals what? Well, not a number.
PQ plus QR.
PQ. PR is just made up of PQ and QR, right? So let's write that. Again, just write what you know. Is it going to be helpful? I don't know. It will for this one. PQ and QR. Colors help. So PQ and QR are what make up PR. You dig? That's all I'm saying. Now, how do I know that to be true? How do I know that the bits of the segments add up to the big segment?
Visually,
Yes, but there's a postulate for that. What's the postulate?
segment something.
Segment addition postulate.
Yeah.
They add up. Segments add up, right? And it's a postulate because it's so freaking obvious, right? Postulates are the things we just have to take a leap of faith on. Yep, as opposed to the angle addition, right? We're talking segments here. Now, what do we know about QS? Let's write that down. We wrote down for PR, QS equals what? It's made up of two pieces. RS and what? And QR. Ah, okay. Do you see how similar these are?
Are you kidding?
Look up here. Look up here. The color matters, okay? So check it out. PR is PQ and QR. QS is RS and QR. See how QR and QR are exactly the same? Now, PQ and RS aren't exactly the same, but why did I do them the same color?
Same angle.
They're kind of
Same measurement. See how they're the same? We know that from earlier. Ah, you see what I'm saying here? This guy's going to equal the same junk as this guy. And if they equal the same junk, then by the transitive property, they are the same. Okay, so here we go. I need this guy to look exactly like this guy. So instead of PQ and QR, I want it to look like RS and QR. So I'm going to write that PR equals RS plus QR. Now, how do I know that I'm allowed to just write RS instead of PQ? Because they're the same. What do we call when we switch out stuff that's the same? Substitution property. So by substitution, I can switch out PQ for RS because PQ is RS. See what I'm saying? They're one and the same. Potato, potato. Now, I forgot to write segment addition postulate again. If you do that, you can just write same dumb thing, right? That's what those two quotation marks mean. Same dumb crap. So now we're here. Now check it out. The two things I want you to be looking at is this and this. Okay, look at that. QS is RS plus QR. PR is RS plus QR. So what do we know about QS and PR? They are equal, which is what we wanted. And how do we know that? We did substitution or the transitive property, whatever you want to call it.
Okay, back. Can I have a pass for you?
Yep. And now we're done. Swag box. See you later. Good luck. Take a gander at these. Try it. Don't try for more than 20 minutes.
I think we're missing something.
The wooden shoe.
That and what did you not say?
Football! Woo! Football! Go get him! Football!
Shoe. It's a moccasin, Justin.
Go get him!
Wooden shoe.
Is it a wooden shoe or a moccasin?
Depends.
A moccasin.
It's a Dutch wooden shoe.
It's a moccasin.
Is that what it's about? It's like a Dutch thing?
I don't know.
Everyone's in this area.
Towns in this area.
Really? Okay.
Like they have a giant windmill in Fulton because
Carpenters.
You want some kiwi?
What?
Want some kiwi?
like you're probably the one teacher that does not call me Carpenter.
Everybody else says
I
Carpenter?
don't even think you talk to me. Like
No.
you don't even say my name.
I refuse to say your name. That's my sister's name.
Really?
Yeah, but she spells with an H on the end.